Hello, this is John. I will show you how to do dynamics on an ELU equipped ship, in this case the 787. First time in fact, so stay tuned.
The first thing to do is set up the cockpit power and hydraulics suitable for the QTG tests. Start JDFC and select the channel you wish to tune, in this example the column. You must run the friction offset compensation for the channel. Repeat for both controls in a paired system. Follow by running the friction sweep to make certain the mechanical friction is not excessive, that is FFMF is not zero. There should be no obstruction in the control travel and no additional mass such as a Fokker bracket. Repeat for both controls in a paired system. The ELU servo gains Ka, Kv, and Kp are typically set to 30 on the first setup of a particular aircraft. They may require fine-tuning later on in the tuning procedure. Repeat for both controls in a paired system. The feed-forward gain K4 is initially set to about 10 on wheels, 2 on columns, and 1 on pedals. You next tune this gain only, and I stress only, via the pull-down KF test. The test will force the control into the hardware stops to determine the current to force characteristics of the channel. The position calibration must be correct and completed before attempting this test. Repeat for both controls in a paired system. When the test is completed, make sure that the value has changed. For the following test, you should have matched the vendor data on the STF, so that the exercise remaining is to compensate for simulator effects so that the final result is close to the STF and vendor data. The control might be unstable, and indeed we want this to tune the resonance suppression gain K4, which capitalizes on the load cell feedback to prevent exciting the mechanical resonance mode of the simulator control parts. The filter frequency KFC0 is best kept at 60 Hz. Give a sharp hit to the control and it should resonate until you touch it again. If not, increase the model page KIMF until you have a sustainable vibration. You can also witness resonance during slow control movement around high slope force regions such as notches, friction changes due to direction change, and hardware stops. Adjust K4 to find the minimum vibration level, the sweet spot as it were. If you do elect to change KFC0, you need to retune K4. Run the Bode test, which will sweep the control over a large frequency range. Select the resonance gain plot from the result to show how well K4 has suppressed the mechanical resonance. Peaks between 3 to 6 decibels are sufficient, as it is impossible to do any better in most cases. Without compensation, the resonance is often 20 decibels. Also check the velocity and position Bodes, which should be near 0 decibels in the lower frequency range. Kv and Kp have marginal influence on this curve since they are servo error terms, whereas Ka does. The dip in response is due to the anti-resonance of the ELU and control assemblies. The position noise at high frequency is an encoder artifact and is to be ignored. When completed, return KMF to its original value. Repeat for both controls in a paired system. The next step is inertial compensation. It is best to start with the bandpass off, even though this video shows the contrary. Start the KIFC tests, which will cycle the control over a large frequency range to determine the most favorable algorithm constants. Run another instance of the Bode and observe the compensation gain result. We strive to get a pass band that is larger, say 3 times, than the content of the dynamics. Most controls has oscillatory behavior in their dynamics that is between 1 to 5 Hz. If the bandpass is insufficient, set the bandpass flag to true, the Zn and Zd damping coefficients to 0.707 and relaunch the KIFC tests. The bandpass can provide more passband if you set the Zd coefficient to as low as 0.4 and rerun the KIFC tests. In the example here, only a small improvement in the passband was achieved with the bandpass filter enabled. Your result should be far better. In many cases, the bandpass enable is critical in achieving a successful dynamical result. Note that the bandpass algorithm causes nonlinear response, particularly emphasizing the dynamical overshoot, which can be difficult to tune. If vibrations persist, tuning Ka and Kv can alleviate them. In general, high frequencies are reduced by lowering Kv, whereas low frequency lumpy fields are corrected with increased Kv. If after all of these steps you cannot achieve a smooth control and this is a repeat ship, consider checking the model tuning over several of the previous ships of the type. For instance, the KIMF may have been tuned beyond a reasonable level over time.
Baby hands up, la 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 la.